Aye, so this is where we get into, I would say, the trickiest questions for differentiation. As you can see, we've got 9 marks for this, 9 big marks. Incredible. So the minute you see maximum, minimum, optimal, things like that, also a diagram like this, you should be thinking, diagrams like this, we've got minimized production, um, minimum value, you should be thinking differentiation because minimum maximums are all about the stationary points on a curve. There's your maximum, there's your minimum. Okay, you're thinking about stationary points. So the first bit of advice I would give you is to take this first question and ignore it because it's very long for 3 marks. Okay, do everything else in your paper and then come back to it. Honestly, it is easy to make a mistake, fraught with peril. I would leave it. Okay, but we're going to do it just now, just so you can have a look. So let's get rid of this first of all. So what we're doing usually is trying to equate two equations together that we know. So this is saying we've got a rectangular plot. Okay, it's got a path, right? And a pond in the middle, okay? X and Y, okay. The total area of the pond in the path is 150. Show the area of the pond is given by this. Okay. So the first thing I'd be doing is trying to two equations together. So I might say, right, though the area, like the total area, is the area of the pond plus the area of the path. That makes sense to me. And I know the full area is 150, so I use this bit of information. So 150 is the area of the pond plus the area of the path. All that, all the pond. Oh, we don't know actually. Yeah, 150 is area pond. Yeah, I got like that. That's good. Can we tell? So X and Y would be the whole thing. So that's also saying, yeah, the whole area 150 is equal to X times Y. So I've got X and Y is the full thing. I know that's going to be 150, and that is the area of the path of the pond. So I could also write that XY is equal to the area of the path. So I'll call that A path. Plus A pond. Yeah, so that's me kind of got a little start then. And I think of something else I could say then. Let's go a bit harder into each of these, right? So the area of the path on its own then, let's look at the path. If I take this area here, this area here, so that's like, area, we'll call that kind of part one, yeah, and then this bit here would be the kind of second bit. Right? If I want to do that, I'll say, well, the blue bit is going to be y times 1.5, so 1.5y times by 2, and to that I'm going to add the red bit, which is going to be 1 wide, it's x long, but it's x take away 3, isn't it? Because I'm going to take away 1.5, take away 1.5, so the length there is x take away 3, that bit, and it's 1 wide, so I times that by 1. That means I'm my length times my breadth, but there are 2 of them, so I'm also going to times it by 2. So the area of the path all in is 3y plus, and if I was to multiply it this bracket, I would get 2x take away 6. So plus 2x take away 6. So that's the area of my path. So let's have a think. Can I put these two equations together then to work out the pond? Okay, so the area of the pond we said here was the area of the path and the pond gives me xy. I know that xy is 150, okay? What about if I said the area of the pond then is equal to 150 take away area of path? So I've just said here, let's take my pond, and I'll do 150 take away that to get that onto that side. So right now I'm not actually use these two. I've taken this equation here, equation 1 I'll call it, and I've just rearranged it slightly. Okay. And I know an expression for the area of the path, I've just worked one. I'll say that's equal to 150 take away all in a bracket, so it's 3y plus 2x take away 6. Right? 150 take away 3y, take away 2x, plus 6 gives me the area of the pond. Now let's see what the question says. Am I close to anything? Doesn't look that close. Oh no, wait a minute. Look at that. Put those two terms together. I've got my 156. Take away 3y, take away 2x. Ooh, so I move right my 2x on this side. Let's write that. So move that over there. Take away 3y. That's close, isn't it? Look at that. Ooh. 156 got that. I just need to get rid of this. So this is saying I need to rewrite y in terms of x. How can I do that? Well, that's where this little equation comes in. So now I'm looking at using an equation. If I just to keep it right, I'm going to call that equation 2. I'm just going to write that in there as equation 2. So now I'm going to use equation 3 because I'm going to say that y is equal to 150 divided by x and rewrite this equation divided by x. Okay. So let's substitute that in. 156, take away my 2x, take away 3 times 150 divided by x, and that will give me 156, take away 2x, take away 450 divided by x. Can you see why we say to leave this? All right, and that's your equation 3. So this one, it was almost actually like using 3 equations to go together. Usually it's just 2, but it's not wildly hard. But I can see why people might get a bit stuck. It's very easy to have forgot, for example, to take off the 3 here. So yeah, you're trying to get 2 expressions. So I knew the full area was the pond and the path, and then I started populating with 150 and thinking about the x and the y, and then saying, okay, well, I've got some dimensions here, so I can work out the area of the path. Let's do the full area, take away the area of the path to give me the area of the pond. Seems simple enough, but there's quite a lot of algebra in that. So that's the first bit. I wonder if I might stop there actually. Let me pause, think. Yes, actually a bit short on time, so what I'll do is I'll write some stuff, pause the video. So the next part of the question, now we've proved the first bit, is to say determine the maximum area. The first thing you want to do is rewrite this equation, so bring your x up, and then differentiate it, and then differentiate it again. We're going to use this to get our nature. So your first step would be to differentiate, and then what we're going to do is work out our stationary point for the turning point. So where do we have that maximum, that turning point, a maximum point on the graph? We'll double check the nature, make sure it is a maximum, yeah, and then we'll get our final answer. Okay, so we'll take our differential, put it equal to 0. We're going to add 2 to both sides, bring the x squared up, divide by 2 and square root. So I've got 2 stationary points here at 15 and negative 15. So I need to decide which of these is going to give me the maximum. So one of them is probably a minimum, one of them is a maximum. I'm looking for the maximum turning point. So which one of these is the maximum? This is when we use our f dash dash. Okay, I think I'll stop pausing it. That should be enough. So when our double differential is less than 0, we have a maximum. Again, I always said it's imagining like when it's less than 0, you get a negative number. This would be like a negative x squared. This would be a positive x squared. So try and get that relationship. I think it's weird saying bigger than 0 is minimum. Also, bigger than 0 would be a maximum, just a bigger number. When this is bigger than 0, it's like you've got a positive x squared, turning point. Less than 0, a negative x squared, so it'd be a maximum. Try and think of that. So let's substitute our 15 into these. This, if I put in my positive 15, I'm going to end up with a negative number. This, 2 negatives, is going to give me a positive number. So this negative number, this is therefore going to be my maximum turning point. Therefore, this is going to be my minimum turning point. So what I'm looking for is maximum at x is equal to 15. So I'm not looking for this other turning point. Then I'm going to finish off the question. So the question was saying, determine the maximum area of the pond. Well, we know the maximum area happens when x is 15 because that is our maximum turning point. I'll take 156, take away 2 times 15, take away 450, divided by 15. And that will give me 96 meters squared. So big question. This is more at the end of your paper type stuff. Ignore the first bit, do that at the end once everything else is complete because you can run around chasing yourself there. At least you know what you're aiming for, to be fair, but it can be hard. Differentiate, double differentiate, get your stationary point, nature, finish.